The speaker is going to be Jaeyong, who is a master student in Sungkyun Kwan University in Seoul. And please, thank you.
Thank you for being here. I'm Jaeyong from Sungkyun Kwan University. I am pleased to present our research, Dedup-for-Speed, DFS, here at SysTour. In 2020, the world produced 64 zettabytes of data. In 2025, it is expected to grow to 175 zettabytes. However, lots of the data are redundant or duplicated. For example, 87% of backup server data is redundant, and 97% of uncompressed Docker Hub repository duplications. Because of this, the duplication is considered as a very effective way to deal with this rapidly increasing storage capacity demand. Flash SSDs are easy to support deduplication. A Flash SSD has a flash translation layer, FTL. The FTL has a mapping table that maps a logical page to the corresponding physical page. The FTL can achieve deduplication by simply mapping logical pages with identical data to a single physical page. For example, let's assume that RPM 5 is stored at PPM 10, and the write request to RPM 7 is just a write, and its contents are the same as the one at the RPM 5. Then the FTL will not write the RPM 7. It will simply map RPM 7 to PPM 10, and that's it. The duplication is done. Because no flash write occurred, the write request will be completed very quickly, and due to the reduced write amplification, SSD's lifespan will extend. Finally, deduplication in an SSD will reduce its garbage collection overhead. But deduplication is not a silver bullet. We know that deduplication significantly slows down the read performance. Modern SSDs improve performance by accessing flash chips in parallel. When you read the logical pages sequentially, the read requests are likely to be processed in parallel by multiple flash chips. But the duplication of a part of a file may impair the internal parallelism. Suppose that we store file once, flow data block. These flow blocks are stored in each flash chip one by one. And this will allow us to read all the blocks in parallel perfectly. But here we store another file 2 also has 4 data blocks. And the second block of this file is duplicated and stored in the first chip. When reading file 2, the FTL must read the second block A after reading the first block E, because they are in the same chip. A few research groups have reported the duplication's negative impact to read performance. For example, 2FTL revealed that the recovery time of a backup system could be slowed down 21 times when applying the duplication, and ZAO found out that the container startup time was delayed by 38 times when applying the duplication to a Docker registry. Finally, according to Lu et al., an SSD with deduplication showed 37% longer read latency for Microsoft traces. We came to the idea that using fast flash mode could mitigate such a problem. As you know, QLC flash cells store 4 bits in a cell, MLC 2 bit, and SLCs 1 single bit. But they have basically the same design at the physical level. What determines QLC, MLC, and SLC is the flash mode. If we program a flash block in the MLC flash mode, its pages will be used as MLC pages. And the less density flash mode provides faster program performance. Modern SSD controllers support the convertible flash mode programming, and Samsung and Micron use SLC mode pages for write buffering in their commercial SSDs. Another basis of our research is the higher the degree of deep duplication, the more frequent the read accesses will be. Suppose that every logical page has the same frequency of read accesses. Naturally, the physical page that are mapped from lots of logical pages due to the deduplication will be accessed by the read operations to all these logical pages. Combining these two observations led us to a simple principle. Let's store duplicated pages in fast flash mode. It will make the read operations to the deduplication pages fast, while the duplicated write will still enjoy the improved performance from deduplication. To do so, we have to determine which flash mode to use for which duplicated pages. For this, we made a simple rule. We choose flash mode to store a duplicated page not to exceed its non-deduplicated capacity usage. Simply speaking, when the default flash mode is the QLC mode, duplicated twice, MLC, and duplicated 3 times, still MLC. But duplicated 4 times, then, oops. Yeah, then let's store it at the SLC block. What about the page duplicated 10 times? There's nothing faster than SLC mode. So, the page will be kept in the SLC page while keep earning capacity savings. The DFS is the FTL that does what I just explained. DFS stores duplicated pages in fast flash mode determined by its duplication count. DFS promotes a physical page to a faster flash mode page when its duplication count reaches the upper threshold. It goes like this. Second right. Yeah. Promotion. The right. Yeah. Nothing happened. But for duplication, yeah, another promotion. DFS demotes a physical page to a slower flash mode page when its duplication count reaches the lower threshold. Animation, okay. In addition to the DD module of conventional deduplication FTL, DFS has another component called the promotion module. In the Dedup module, there are three important data structures here. First, fingerprint store stores hash values of physical pages. Duplication count table stores each page's number of duplications. Picture table stores the inverse of logical to physical table the FTL manages. It stores physical to logical page number mappings of the duplicated pages. These data structures are already in the existing deduplication FTLs, such as Remap SSD. Now, when a write request arrives, after performing inline deduplication, the promotion module checks the duplication count of the corresponding physical page and put the physical page into the promotion queue to promote it. Once the physical page number is inserted in the queue, the actual promotion of the page will be handled during idle time, not to interfere the host issued I/O operation. The inline deduplication mechanism here is basically the same as the ones published before. In DFS, a valid page moves to a page of proper flash mode during garbage collection. Therefore, queued promotion and demotion may occur during garbage collection. An example is shown in the figure. An MH block is selected as a victim block for garbage collection, and DFS checks the duplication count of its pages. A page with duplication count of 2 is migrated to the MH block, and a page with duplication count of 1 is migrated to the QH block. This is demotion. And the page with duplication count of 4 is migrated to the SS block. This is also promotion. Yeah. Shown is the evaluation environment setup. We implemented the DFS in SSD sim. The table presents the time taken for each kind of operation used in the simulation. We compared DFS with the original FTL denoted as no dedup and Remap SSD denoted as dedup. We used the three types of workloads for evaluation. Hypothetical workload is synthetical workload following the ZPN distribution. And second, we also used FIU traces. They are used by a few deduplication researches. Finally, we used in-house VDI traces. We analyzed the read performance improvement depending on some parameters with hypothetical workloads. In the graph, the x-axis shows 3 different deduplication ratio and 3 different read sizes. The y-axis is normalized with the latency compared to no dedup. In all cases, the DFS performed better than no dedup and dedup. However, since data duplication was determined in unit of 32 kilobytes, DFS broke the sequentiality. So, as the read size increased, latency of both FTLs increased. Also, as the dedup ratio increased, dedup FTL performed poorer. Because in dedup FTL, more deduplicated pages resulted in less sequentiality. But DFS performed better because the duplicate data were read in fast flash mode. In the 70% of dedup ratio, 75% of data were read in fast flash mode. The latency was 38% lower than that of no dedup. So we can say the higher the deduplication ratio, the slower the read performance in dedup, but the faster the read performance in DFS. Next, in the analysis of real-world workloads, we hoped to prove that DFS improved read performance. The left figure shows also normalized read latency, dedup extended read latency by up to 23% in VDI traces, which are 3 on the right. Dedup showed increased latency caused by degradation of sequentiality. DFS, on the other hand, maintained a lower latency in all scenarios because fast flash mode was used in some proportion. The right figure shows the normalized number of reads in each flash mode. We can conclude that the performance gain from DFS is proportional to the access frequency to the fast flash mode pages. To analyze the effect of using fast flash mode, we checked average number of reads per page on each flash mode. As shown in the figure, in most scenarios, pages in faster flash mode were read more than that in a slower flash mode. Particularly, the second scenario of home, SL's pages were read more than 7 times on average. In conclusion, this proves one of our rationales. The higher the degree of duplication, the more frequent read access will be. Additional writes caused by promotion and demotion may degrade the write performance. In the figure to the left, write count of DFS increased up to 196% compared to dedup FTL. But still, it was only half of no dedup on average. The additional write did not affect the host write performance because they are handled during idle time. The right figure shows normalized write latency. As you can see, dedup and DFS showed no difference in write latency. Another concern of ours was about space usage. The additional write to fast flash mode also decreased the capacity of the DFS. We have inspected the amount of space used in each FTL. Compared to the dedup, DFS did use a little more space, but it never used more than no dedup. In the image scenario, here, by giving up 26% of capacity earnings, DFS could improve read latency 70%. In conclusion, duplication in an SSD not only reduces write latency but also saves place space. However, duplication may degrade the read performance. Therefore, we proposed the novel deduplication FTL, DFS. By storing duplicate pages in fast flash mode, DFS uses a portion of additional space earned from deduplication for the sake of improved performance. As a result, while maintaining the same level of write performance as the SSD. DFS also improved the read latency in the real-world workloads. Thank you.
Thank you. We have time for a few questions. So, Mickey.
Simple one. Is there, now you have to divide blocks into blocks with SLC, QLC, LC. So that reduces the amount of QLC blocks. Is there an effect on the lifetime of the device now? Because there are fewer blocks used for QLC. And the blocks that you are using for SLC are those with high duplication, so they're not going to be erased, probably.
Yeah.
Is there a lifetime effect on this?
I don't think I really understand your question. Please repeat again.
So, is there an effect on the usable lifetime of the device?
Yeah.
Because this scheme reduces the number of blocks available for QLC.
Yeah. I think I need some help. Yeah. QLC가 줄어서. I don't think there's no bad negative effect of using QLC and MSSLC because QLC have the shortest lifetime, and SLC has more lifetime because they can more erase cycle is allowed to SS mode, and also the reduced write by the duplication will get positive effect for the SSD, yeah, because there are no duplicate writes.
Have you tested this without local deduplication, and if you're not using the single device deduplication but a flash array with file system deduplication? Does that also benefit from this scheme?
I think I need another help.
Maybe we should take off the mask.
Yeah.
If I understand correctly, this all works on the single device. You're using the hardware duplication the controller, if I understand correctly. So, can software in a flash array using the file system duplication without hardware controller also benefit from this?
I think if we have the duplication count from the file system, we can use that. And also remember SSD that I mentioned here can some get help from the file system.
But typically, if you do dedup at a higher layer, you don't have access to choosing SLC, MLC, etc. That's an FTL level thing. So I'm not sure you'll have the API. But
yeah, but it could be implemented to the driver, I assume, if that was the demand.
yeah, that's good.
Define two drives each in one vector.
Okay. Yeah.
Why don't you just remove the deduplication part and just use it as a way to cache highly read pages in SLC and just do that? What if you just don't do the ignore the deduplication?
But
maybe someone has done that.
as I proved here, if we store the duplicate pages in the SS page, the effectiveness of the using best flash mode is high. So we used this.
Right?
Okay. So thanks. Let's thank the speaker again.